Okay, so the reason I wanted to show you this is because I I can't leave anything alone. I have to keep updating it, making it better, and all that. So you'll see I've added, for people who haven't looked at it recently, I've added a bunch of stuff right here. I'll go over this today in the lecture, but I also added stuff here, and I predict I'm going to be adding stuff further on later in a little bit. But anyway, I wanted to let you know that the syllabus is a living document. I've also linked in, for people who want to follow along, this right here is a link to the presentation today, to the first one, and this is a link to the second one. Okay? And I can see all of you up here, Anonymous Frog, Anonymous Anteater, and Anonymous Manatee. I see you. Okay, so let's get started, okay? So let me go here and start presenting. So this is fun. It's 8 o'clock in the morning here. I know it's 4 o'clock in the afternoon there, but this will be awesome. So this is lecture 11, and what we're doing is, in the whole sweep of this class, we're now sort of in the middle of talking about how do we analyze social computing. We'll be talking about network analysis, but also about sort of social behavior analysis. So I want you to keep that in mind. There's basically two kinds of social computing analytics that we can do: network analysis and sort of aggregate behavior analysis. And we'll be doing both of those. So let's go. So our key topics for this first hour are basically these papers. And as you see, I added a couple. So if you didn't look at the syllabus in the last week, you've missed the update there to We Feel Fine by Jonathan Harris and Sepp Kamvar in the bottom one, Information Wars. I know at least some of you read it because I got some notes from people saying, that was kind of cool, thank you. But we'll talk about what Kate Starbird had here in a minute, okay? So today, it's basically, for this first hour, we as actors in the computer systems, in the computer networks, leave all this, what some people call data exhaust, or information trails, or life bits, or whatever you want to call it. This is all about how do we understand that aggregate behavior. And then the last one there with Information Wars is about how people behave in large scales in network. Okay, that's the first hour, okay? So let's talk about that first paper. Now, if you looked at the paper, it's an odd paper because it actually appears in multiple places with slightly different names, whatever. One of the things the big point it's trying to make is that if you basically think about computational science and social computing as a real thing, what can you learn? If you aggregate all this stuff together, what can you understand about the emotional life or about the day-to-day life of people at a large scale? Now, this is the list of authors, and you might be wondering, what is going on here? Why are there so many authors? Why are they from so many different places, and what's going on? So this is a paper in Science, which is one of the top 2 or 3 journals in the world, scientific journals in the world. And this is a classic sort of position paper. That is, it's basically putting a stake in the ground. It's basically saying, look, here's a new area of interest, a new scientific research topic, and we should be paying attention to it. Now, you see it Harvard, MIT, Michigan, NYU, all these different institutions. Let me tell you something. Remember we talked about all these people before and how they're all connected? Yeah, that's true here too. So these people all have either worked together or have been students together, or they're all in the Cambridge MIT universe. So you see, for example, David Laser at the very top from Harvard knows Sandy Pentland at MIT, who used to be, who was, Lada Adamic used to work at MIT. Used to be at Michigan. She's been at Facebook, and now, et cetera, et cetera. I can tell you a story about all these people. So the interesting twist here is that all these people are connected by a social network. So that's how they're all on this paper, and it's really sort of the first big paper to appear in a big journal about this whole area. So that's what's going on. That's why there's so many authors. So the point of the paper is basically, look, we're all shedding data like skin cells, dandruff on the floor of computational reality. And so this paper is basically arguing we could do something with this. We're shedding all this stuff, but it kind of depends on what kinds of analysis you can do. Who's got that data, and what kinds of things can you do with it? So the scope of the work that they're describing really depends on the kinds of data you have, the resolution of that data, and how you can interpret it. So that's what I mean by the type and the quality of the data. So for example, Deb Roy, who's like the 10th author, has been working on this thing he calls the Human Speechome Project. Now it's a pun on genome project. What he did is, you see the picture on the left? That's a sort of fisheye lens view of his living room. And if you go to that URL, you can actually go and watch, his entire life for basically 10 years. I'm sorry, three years of 10 hours per day of multiple cameras in his home, recording everything his child, who was newborn, the first 3 years of everything that kid said. So it's an amazing, amazing thing. And now he's got hordes of graduate students who are transcribing this and so on. The point is that imagine that you had perfect transcription. What could you do if you had a longitudinal data set like this one for watching how kids acquire language? And in fact, I took this frame out of a QuickTime movie he has on his site, which is, this particular one is about how his child learns how to say the word ball. And you can hear him going from woo, woo, ba, 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 ball by the end of the movie over the course of about 6 months. It's really an interesting approach. I think for us, the lesson here is, what does the data set allow us to do? One of the things we all, and I bet 3/4 of you in the class do this, is we all do various kinds of things with quantified self, right? Don't you? I do. And so I can look, for example, at my quantified self to see how many emails I've sent per day. If you have a Fitbit on, just quick question, how many of you are wearing Fitbits or some kind of motion tracker, right? Okay, that's some number. But you can look at all of this personal data and actually then see what you're doing as an individual. More interestingly, what do you do if you can aggregate all that data? So you see in the upper left, 11 followers. So this is a kind of a not highly connected person, but there are 11 followers who are tracking this person's data. And in turn, this person is following 5 other people. And it's taken remarkably 88 pictures of food that they've eaten this week. So this is interesting, but it's more interesting when you can start to aggregate this whole data. Suppose we could actually aggregate data for an entire country or an entire region about, say, health and movement and so on. That's kind of where this whole first hour is going. What does it mean if you can gather that data, analyze it, aggregate it, and come up with insights? That's what the paper's about. So for example, as you probably know, Google and other companies track the motion of their cell phones, the Android or the iPhone or whatever. The GPS locations are all tracked. You can turn this off if you want, it's under settings. But if you leave it on, and the default is on, what this does is it anonymously provides motion data around city streets. Okay? What this does is allows us to create graphs like this. So each color here is a different day of the week. And I bet that purple one on the bottom is Sunday, because 10 a.m. on a Sunday morning is probably pretty quiet. Whereas I bet the blue one is probably Monday morning. I don't have the legend here right now. But once you start to see this, you can start to actually make very sophisticated models of traffic patterns in cities, which allows you to do much, much better traffic planning and route planning. And you can also see there that dip. Can you see my mouse? Yeah. So right about here, you see that sudden dip? That's, of course, noon, right? But there's no change in the pattern on that bottom purple line, which is Sunday, and not much of one on Saturday either. So this allows Google Maps to give you time-varying route directions. That's how we can do it. So, for example, if you want to say drive through the center of Zurich, we can actually know hour by hour what the rough flow is, say right by the Hauptbahnhof. We can tell you what the flow rate is going to be. Now, this has an interesting side effect, which is that there's been pushback from local communities because, for example, the street I live on is just one street off, one street parallel to a very busy street. And so when people are trying to get somewhere very quickly, they will often be routed by Google Maps down my nice, quiet, residential suburban street. That's annoying. And so you're seeing this interesting social dynamic where people in neighborhoods are pushing back against the aggregators of data. Nevertheless, if you're trying to do transportation planning for a city or a region, this kind of data is really useful. So let me give you this word which is becoming increasingly common these days, which is called datafication. Now, datafication means taking images or data that was in an inaccessible format before. Say, on the upper left here, you have an image from Google Earth. What you can do is, if you can write sufficiently smart code, you can then do extraction of that image, of data from the image, and relabel it as actual data. That's the datafication process. So converting, in this case, an image from Google Earth into a map of actual high-resolution vegetation locations. Or you can see in the bottom two rows there, identification of buildings and of plants within the local areas and so on. So there's a nice, if you're interested in that sort of thing, there's a nice paper from 2012 linked to on the right. But datafication is this process of taking this data that was previously inaccessible and converting it to something that gives you sometimes surprising results, like this one. This one was done by Sabine Begal, and I forget where she's at. I think she's in Germany, Leibniz, I think. Anyway, she did this amazing thing. She wrote a piece of code that would extract the orientation of cattle and deer. So cows and deer that are grazing in green fields, say in Switzerland or Germany or France or United States. And it's relatively easy to write that piece of code. And then she computed the actual northwest, southeast orientation of these animals. And here's the weird result. It turns out that at different times of day, for example, at the B plot in the middle, most of them are pointing just a little bit off of north or south, because she can't tell which direction the head is pointing. But nevertheless, the cows are pointing north. This is datafication, which gives you a very, very surprising result. And she says in that paper, if you read it, it's a fascinating paper, that they don't know why this is true. They're bet it's something to do with solar radiation and trying to soak up the rays or something. So when I read this paper, I had this image of all these cows in Switzerland sunbathing at noon and trying to align themselves to the north-south axis. This is actually another example of that datafication process. If you've got a few minutes, I highly recommend you search out this page and go visit their website. I forgot to put the link here, but it's easy to find. Because the videos on that website are just remarkable. Don't do it now. Don't do it now. Wait till the break. The thing that they realized is this is work with University of Washington and folks here at Google. And somebody at Google said, hey, you know, there's a lot of images on Google Images. And there are a lot of repeated images. But when they started looking at it carefully, they're not actually repeated images. So you see this picture of that glacier, those five frames of the glacier? Those were actually taken by different people on different days. What they realized they could do is they could extract the metadata of the time of the image and then warp the image to match a previous image or a post image taken by somebody else on a different day. You see what you can do? You can datafy the images in Flickr or Google Images or whatever. You can write a crawler to go pull out these images of, say, a Lombard Street in San Francisco, or in this case, a glacier. and then create a time-lapse movie over years. And the interesting thing is, no one person took that video. It's composed. It's created, right? I mean, this is a remarkable thing. And these videos are just astounding. But like I said, don't do it now. Wait until the break or wait until after class today. But this is a datafication of an interesting kind. Now, you can imagine then, for example, extracting glacier flow over years, which is something that would have not been previously been possible. So, fantastic result. That's a great paper. Go read it. And of course, now returning to social computing, well, wait a second. That previous thing is social computing. It's just they didn't know they were being social, right? They didn't know they were contributing to this aggregated video, this time-lapse video. And you see, when you start to look at millions and billions of transactions happening on the web or in the internet, you can start to see patterns like this. This is actually not a map of the world. This is a map of endpoints of Facebook messages. So what you see here is actually unpopulated regions don't show up. So for example, looking at above the United States, you can see the upper strip of Canada, and beyond that, there really isn't anything because nobody lives up there with a cell phone. Or for example, there's big chunks of China and Russia that don't have much. I can see Moscow there, that center node here, but a lot of Siberia, there ain't nobody out there. But you can start to see the emergent pattern, the heavily messaged pattern here in Central Europe. And this, if you zoom in, you can see this sort of dark area here. I can guess what that is. I think you know what it is too. But you see what happens. When you start looking at millions and millions of pieces of information from multiple people, all anonymized, you start to see remarkable things. So one of the folks in that paper, in this big science paper, is Lada Adamic. I know her because we both worked in the same research lab for a while. And she did this really brilliant analysis of blogs in the US, this is only US, blogs in the US and the connections between them. So these dots are connected more closely if they have similar kinds of topics that they write about. So the red nodes on the right are the political right in the United States, the Republicans, the conservatives, and so on. And on the left are the blue, liberal, democratic, and so on blogs. And what you see here is that there are a few nodes that are close together, and the yellow ones are the connections between certain blogs in the liberal spectrum and certain blogs in the conservative spectrum. But these blogs talk to themselves, right? The dominant data here is that there's an emergent structure of connectivity patterns. Keep this in mind. There are two things I want you to think about here. First off, this kind of granular structure where you have two sort of hubs, two sort of strongly connected components of the graph. We're going to come back to this next time we talk. We'll come back to talking about how we compute these sort of centers. Second thing to think about, you're going to be doing a data analysis project here not too long. When she did this analysis, there were no colors in the graph, right? So she dropped in all these blogs, computed the correlation between the texts, and had it run the force-directed map to create this graph structure. And then she said, oh, look at that. There's a strongly connected component here. There's a strongly connected component here. And then there's these bridging things. I'll call the bridges yellow, and I'll call the blue, the left-hand component, and so on, right? It's an accident that blue is on the left, and left is political left as well. Or maybe she did it on purpose. I'm not sure. I should ask her. But nevertheless, think about this. When you're doing your analysis, nobody hands you the interpretation. You have to come up with that on your own. Okay? I left a slide in here. I forgot about it. There we go. So ignore that previous slide. That's just a leftover. One of the things that's really well known in social network analysis is this notion of personal connectivity. So you might have heard of your Bacon number or your Erdos number. So this is basically this commonplace notion that everybody's connected to everybody else. by a small number of links. This is the idea that everybody in the film industry is connected to Kevin Bacon somehow. And so here's a website, the Oracle of Bacon. I'm not making this up. You can go search for it. And I just typed in Kate Winslet as somebody. And you can see the graph here on the left. Kate Winslet was in the movie Labor Day, and she also in that movie was J. Parker Kent, who was also in R.I.P.D., who was also with Kevin Bacon. So the connectivity pattern here is degree 2. 1 link, 2 links. Now, in the scientific community, there's also this notion called an Erdős number. So, for example, I think my Erdős number is like 9 or so, which means I wrote a paper with this person who wrote a paper with that person who wrote a paper with that person. And basically, the entire universe of scientists and mathematicians is within degree 9. So I'm not very connected. But nevertheless, the actress Natalie Portman has an Erdős number of 6. Go figure. Turns out she actually wrote a paper with somebody at Harvard who wrote a paper with somebody and so on, right? Here's the point. Social networks have a lot of information in them. Sometimes it's path connectivity like this. Sometimes it's the aggregate behavior like we saw earlier. And part of social computing is figuring out how to extract and analyze and understand this data. Because one of the challenges here is there's all kinds of secrets here in the data set if only we can get them. So in the US a couple years ago, there was this really famous scandal called the Enron energy scandal. Enron was a big company that basically did a bunch of very shady deals, and it was just a giant disaster. They finally went belly up, and they declared bankruptcy. And as a side effect of the lawsuit against them, the entire email corpus for the entire company, since its inception, came out. And this became somehow magically available online, and everybody I know grabbed a copy instantly. So I still have a copy somewhere. And it's been, I'm sure the people at Enron were really pissed off about this. But it allowed people like Jeff here, who you see, he did a visualization here. I did a visualization too, but his is better than mine. So this is the pattern of people inside the company, inside of Enron, who sent email to each other. So this is very much like the blog analysis we saw earlier. Remember that? With political red and blue. This is the same kind of thing. And if you zoom in, look around, you can see these deeply connected patterns. So for example, there's one little cluster of people here. This is a department within Enron. Here's another department. Here's another, you start to see that. You start to see these other departments. And this is, you can see, it's a little hard to see, but there's a pattern right in the center of it, which is sort of the executive management stuff. And if you drill down inside of this, you can start to see all kinds of interesting social network patterns. And this is from real data. This is several million email messages. Interestingly, you also see out here a bunch of people that only ever have one email. And these poor people who never got anything. These are clearly people who were just around for a day or something. They never actually got any email. But once you start to understand the power of social network analysis, you can start to see structure in here. You can start to see what's happening and what's going on. I will tell you from my own analysis, those guys were guilty. I mean, it was just horrible. And it's remarkable how much information you can get out of a corpus like this. There's a last sort of social network graph I wanted to talk about, which is, so I got my PhD in 1984 at the University of Rochester. Who was my advisor? Well, I had 2 advisors, Jerome Arthur Feldman and Christopher Montgomery Brown. Now, the Mathematics Genealogy Project is a project that has datafied PhD theses in terms of the relationship of advisor-advisee. So I was Jerome Feldman's advisee. He was my advisor, right? So if you go to this website, you can actually, just by clicking on the advisor, 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 you can go all the way back and discover who your great-great-great-great-great-great advisor was. And my great-great-great-great-great-great advisor was Euler. who went to the University of Basel. So he was kind of a local guy. And there's his dissertation topic. And it turns out, you see down here, Joseph Lagrange. So Lagrange was Euler's student, right, in 1730 or something. It doesn't have the year here, but we could go look it up. It turns out that he's got a lot of descendants. So Euler had, 1, 2, 3, 4, 5 students. Lagrange had a lot of students, and they had a lot of students, and so on, and so on, and so on. So the network structure below Leonhard Euler concludes me. And of course, if you wanted to check, you could click on this link right here for Johann Bernoulli. Yeah, that Bernoulli was Euler's advisor, right? Anyway, this is a kind of social network which was, again, datafied out of the online databases of PhD theses. Okay, that's that first paper. Basic summary is this is an important area. We've got a lot of work to do, all kinds of interesting things going on. Cool. Now, not that many years ago, Sepp Kamvar, who used to work with me here at Google, and Jonathan Harris, who's a friend of his back, I think, at MIT, did this really interesting analysis of Twitter stream. Now, we're going to come back to this notion of analyzing the Twitter stream, and I want you to think about it because the Twitter stream is an interesting data source for you to think about in terms of analysis you might want to do. So pay attention. This is kind of an interesting example. And what they hypothesized was that if you aggregate all of these tweets coming out and do some basic sentiment analysis, that is, was this person happy, were they sad, or just what are they saying things that are aggressive or unhappy or anxious or whatever, what would that tell you? This is a fascinating project, and basically what their method was that they wrote a piece of code, a little cron job. Every 10 minutes we'd wake up and we'd go and search for tweets that contain I feel something, I feel star, or I am feeling star. They basically would save that in their data set. Then later, offline mode, they would scan through each of those things, each of those sentences every day, and look at one of a couple thousand pre-identified feelings. So these are basically adjectives or adverbs that they have identified as being indicative of anxiety or happiness or depression or whatever. And then they had a color mapping. Okay? Now, when they took out that sentence from the tweet, I am feeling unhappy. I am feeling ecstatic about the state of man, or whatever that sentence is. They also, at the same time, grabbed the profile page of the author. Okay? Now, a lot of those profile pages have age, gender, country, state, so on. And if you know that information and you know what time that tweet was made, you can also go out and grab the weather condition. Aha! Interesting. So if you're a database person, you would say what they're doing is doing a join of two different data sets, two different database tables. They're joining weather with the location which is identified from the tweet, right? Does that make sense? So this generated 15 to 20,000 sentiments per day. Then what they did is they created these beautiful visualizations. And unfortunately, I can't show it to you. If you're interested, go check out their website. You have to download Java to run the applet, but it's fascinating thing to look at. It's also really beautiful. You can waste several hours fooling around with this. But what you're seeing here is at the top is a tweet of the type madness. You see in the lower left corner there, it says madness. So these are different kinds of visualizations of different kinds of data. But what they're doing is they're extracting and then displaying in this sort of infinite star field different people who are unhappy about the world. This is being mad about things. And you see there's this cluster here. If this were interactive, you could roll over these dots and see the sentiments that are being expressed. This is English only, I should point out. They've got a lot of different visualizations. This is a way of looking at the different kind of sentiments. So if you clicked on, say, lucky, I could go see all the lucky things and see who's saying that and how they're oriented or organized and so on. You can compute for a particular location if people are feeling crazier or happier or whatever. And you could drill down. I could say, how are people feeling in Zurich this week? And you might find, if it's been a particularly rainy week, that they're feeling sad or unhappy, whatever. I remember that. We just hypothesized a connection between the weather and the affective response in tweets. We're going to come back to this in a couple of papers, so remember that. So they also can do things like, if you look at gender and you break it down, men versus women, this is a fascinating chart. 1 million feelings were expressed in their data set from roughly almost 2 million women, but only half as many from the men. This, I know it confirms a gender stereotype, but this is what they measured, right? Stereotypes are stereotypes often for a reason. So where they're going with this is, for example, if you look at expressions of happiness and unhappiness, this is looking at happiness, or the blue ones are unhappy expressions. And you can see during this particular time period, you see this column here in sort of the left center. There were a bunch when it was cloudy, fewer when it's rainy, and even fewer when it's snowy. And of course, you get nothing but positive expressions when it's sunny, right? Very few negative expressions. Again, remember this, because what they did, they really called it an art project. So this visualization and the visualizations they created, the interaction they created, was installed at a museum in Cambridge, Massachusetts, for quite a while. It got a lot of attention, a lot of people wandering around, trying to understand the affective response of the world. Fascinating work. But there was never there was a beautiful book published, but it's basically a coffee table style book, something you'll look at with friends. Not a scientific result. But I wanted to show it to you, give you an example of the kind of stuff that can be done. Now, this third paper I wanted to talk about because it's probably one of the most notorious, it's certainly one of the most recognized papers in all of social computing over the past several years. And it's not known for a great reason. It's known for being notorious. I'll tell you why. So the title is, it's another paper in Science, Experimental Evidence of Massive Scale Emotional Contagion Through Social Networks. Okay, it's social computing right at the beginning. It's a little bit about how people represent themselves. Sorry, it says Twitter there, I meant Facebook. Let me tell you how this works. It's an emotional contagion study. Now, what I mean by that is that they're asking the question, can a small change in the Facebook feed, these guys did this study of Facebook, can a small change to that Facebook feed cause an emotional reaction in the users? What do you think? So let's unpack that abstract a little bit, and then we'll look at the data in just a second. Okay? Let's unpack it. The first thing to remember, they said, is we test whether emotional contagion occurs outside of in-person interaction between individuals by reducing the amount of emotional content in the newsfeed. Okay. Emotional contagion is basically this effect of sharing. They call it contagion, but it's basically, I walk down the hall, I see you, I smile. You smile, you're happy. I have just been contagious for happiness, right? Or if I'm walking down the hall and I'm really pissed off about something and I'm frowning and my body language is negative, that transfers to you. So that's what they're trying to test. Can emotional contagion, that is, emotional affective responses, be shared between people not using in-person interaction? No, if we see each other in the hallway, that's in person. If you just read my Facebook post, does that change you? Does that affect you? So what they're going to do is change by reducing the amount of emotional content in the person's newsfeed. Okay? Here's what they think is going to happen when they read. Well, this is the abstract. So this is what the summary of what they're saying. When they reduced the number of positive expressions, people created fewer positive posts, and more negative posts. The opposite is also true. When negative expressions were reduced in the newsfeed, the opposite pattern occurred. Okay. This tells us that the emotions expressed by other people on Facebook influence our own emotions. And so this is basically giving experimental evidence for massive scale contagion. Okay? That is, it has broad effects. And that's part of the thing that, remember, these people were working at Facebook. They're not all from Facebook, but they were all working there that summer. This work suggests that in contrast to prevailing assumptions, in-person interaction and nonverbal cues are not strictly necessary. They said that because there's this whole body of literature that says you need to be face-to-face. If you just read it, it's not a real affective response. So there's a whole pile of philosophy behind this. They're basically saying in that sentence, you guys, you're wrong. It's not necessary to be in person to have an emotional impact on somebody else. Now, we, you, me, we are all children of the media age. And so this is sort of obvious to us, but the literature says this is not true. Anyway, this is a fascinating result. So here's the thing to remember. Yes, I know this is Twitter, but yeah, same idea holds. Our feeds are different, and that's what they did. They wanted to take advantage of that because no two people's feeds are identical, and they wanted to do something with the feeds to manipulate it. So what their question was, if you boil all that stuff down, the research question is, are emotions contagious in text-based interactions? That is through Facebook. Okay? Now, there's the definition of contagion. I just told that to you on the left-hand side. It's been studied for years. And the research problem has always been that they use a couple of undergraduates in a Midwestern university in the United States, or they do it, a couple of undergraduates in France or whatever. It's not a very big sample, and it's usually inexactly coded. So the data itself is kind of suspicious. Good. So suppose you're now at Facebook and you're a research scientist. You say, I wonder if this is true. What can we do? So what they did is they did two different experimental treatments. Okay? So that's what a treatment is. You're going to change something in that person's experience. So they had two, A and B. In the first one, they omitted some fraction of all the positive posts. Okay? Now remember what Kamvar and Harris did? They had this little analysis tool that would say, here's a tweet. Is it positive or negative? They use something very, very similar here to say this post is has a positive affect or negative affect. So a positive affect would be something like, I'm so happy today, all my spring flowers are blooming. Yay! Right, that kind of thing. A negative one would be, I'm so unhappy today, all my spring flowers have been destroyed by snow. That kind of thing. So it's the language. They wrote a piece of code that analyzed it in terms of positive and negative. And they, of course, had controls. And they had the set of people that they monitored at the same time in the same group, in the same time zone and everything, that basically they did nothing to. Okay? That makes sense so far? Good. So their hypothesis is, if affective states are contagious, if that's true, then people in the positivity-reduced condition should be less negative. Okay? What that means is what they're going to do is turn down. If you're in the A group, I'm going to turn down. I'm going to not show you all those positive Facebook posts that your friends are doing. I'm just going to let the other ones come through. Okay? They're going to be less negative. They're going to be more negative on whole. Okay? And so what they propose as a dependent measure is to check the number of positive or negative posts that person makes. Okay? I'm going to delete some of the positive posts, and you should, as a consequence, write less positive posts. They should be, right? Here's the result. This is the big chart. Okay? So the way to look at this is that, let's just consider the top row for a second. So the dark blue are the control people. These are the people, this is their normal response. So the chart here is the number of positive words percent in their posts, okay, during this time period. And it turns out that control people, it's like 5.24 or something like that, right? Percent of all their words, all their posts are positive. Got it. Now, in this experimental group, this is the negativity reduced group. That means they reduced the negative posts. So they took out all the bad ones, or most of the bad ones, right? And guess what? Those people when they see fewer negative things, they write more positively. That's why this light blue chart bar is above the dark blue, above the control. Hey, fantastic! This means that if you cut out the negativity in your Facebook feed, your subsequent posts are more positive. Okay? Let's go over here and look at this one on the right. This is the reverse, basically. Again, the control group. So basically, again, 5.4, 5.5. This is the positivity reduced. That is, they took out the positive posts. And guess what? You write fewer positive control. That's this group that writes fewer positive posts. Okay, so that makes sense. If you see fewer negative things, you write more positively. If you see fewer positive things, you write less positively. Okay, now, oops. In the bottom chart, we're seeing the negative words, the number of negative posts percent. And again, the control group is about 1.75 or so. Same thing holds here. If you see fewer negative posts, you write fewer negative posts. And the same thing for positive. If you see more positive posts, then you end up writing more positive posts. This all makes sense, but it's showing the hypothesis is true. However, there's a gotcha. You knew there would be a gotcha. There are actually two. Here's the first one. The first one is that effect is really tiny. Okay? Yes, it is a statistically significant effect. But look at the numbers here. Let's consider just this negativity reduced one. The control group is at 5.5%. No, 5.24%. And the experimental condition is at 5.27. That means that the difference between those two, if you assume that those averages, the tops of the bars, are true, the difference is like less than 1%. It's like not even 0.5%. So this is a tiny, tiny effect. And it's interesting to note that if you run this with fewer than, say, a couple thousand people, there's no way you're going to even see this effect, probably, right? The effect itself is tiny. So this is cool, right? I mean, it's kind of a neat experiment. That's not why I'm telling you about this. It is an interesting result, but it's not why I'm telling you about this paper. The second, sort of another interesting side effect was that there's also a withdrawal effect. So after people who were in the treatment case, after it stopped, people that were exposed to fewer emotional posts were less expressive. So there was a kind of, oh, you stopped futzing with it, so I'm not going to write as much. Fine. That's sort of an interesting subtext result. However, the real reason I bring this up is because people really got upset about this. And I mean, there was a major scandal in the community. In fact, if you printed out the paper, there was in the first page a notice from the publisher. What did it say? I got to pull this up because it's such an interesting thing to see. The very first page, if you printed it out, was an editorial expression of concern and correction. What? Well, if you read that carefully, basically what happened was that they did this study, and then the results came out, and there was this big wave of negative publicity. And here's an example article at the time. Facebook study sparked soul searching and ethical questions. So why were people so unhappy about this? Well, what was going on was that people, and there's a whole list of all of them, if you want to go read it, it's sort of sad. The emotional contagion study revealed to people on Facebook, that is the users of Facebook, that they were collecting data without informed consent. Now, have you heard this phrase, informed consent, before? Whenever you do a psychological study, anywhere, this is true now, it wasn't true, say, 20 years ago, you now have to get informed consent. That is, that the participants understand what's happening, what will happen with their data, and all that, okay? Now, Facebook was futzing, it was mucking around with the Facebook feed, and they didn't ask for permission ahead of time. In particular, the point of the study was to manipulate people's emotional response. And people found that very deeply disturbing. Right? So the truth is people, big companies, Google, Microsoft, Facebook, you name it, we all run studies constantly where we are varying conditions. We call them A/B studies. Right? The thing that really upset people, though, was two things. A, that the subject was a changing emotional response. The second thing that was really surprising to people was that Facebook was not showing you all of your data stream. So Jeff Hancock, who was one of the authors of the paper, gave a brilliant talk, I think, last year at the CHCW conference, and he talked about why there was this response. Basically, what happened was, was that people did not realize that their feed was being tampered with. Now, if you think about this from a computer science perspective, there's just too many pieces of data coming into your data feed, your Facebook news feed. They have to rank order the things they show you. Google does this all the time. When you do a query and you get a million results back, we could give you 1 billion results, but we are going to only show you the top 1,000 or whatever the number is. We rank order the results. Facebook does the same thing. Twitter does the same thing. Instagram does the same thing. We all do this because the unfiltered data stream is too big. It's too fast. It's too much. But most Facebook users, when you ask them, believe that they're getting the full stream. They're seeing everything that their friends are writing. It's not true. So that really pissed a lot of people off. So it's about 8 minutes till, and I don't want to shortchange Kate Starbird's paper. I want to spend at least a couple. We've got time. We've got time. Let's do it. And then we'll take a 5-minute break and we'll go to the second section. So Kate Starbird is at the University of Washington, and she's studied for years what's called crisis informatics. Okay? In particular, what that means is that when a disaster happens, say a hurricane hits a Caribbean island, or an earthquake strikes, or a tsunami hits or something, that's a crisis. And as you know, in a crisis, lots of people start tweeting, they start posting messages on Facebook. Facebook brings up their I'm Safe Now page, et cetera, all that stuff. So her work for the past several years has been to try to understand how people behave when crises happen. So this paper is basically an analysis of the rumors, that is, the speculation about what's going on, often that borders conspiracy, about what's being said and how it's being passed around. And she does, well, let me back you up. I have to tell you the story. Like a month before this piece came out, I visited Kate Starbird. She's a friend of mine. You knew this. So I went to her office, and we were talking about this kind of stuff. And she was just really beside herself. She was unhappy because the fake news stuff in the United States is getting to be big, and this rumor control and conspiracy theories are being passed around. And she said, I can't believe I've never paid attention to this. I mean, she was really distressed about it. And so this paper basically was a response to that recognition that there was this interesting phenomena in the social media and how it was being passed around person to person that she had never noticed. She went back and looked at her data, and yes, it was always there. So, for example, there's a crisis. The Orlando shooting in Florida a few months ago. And what she noticed is that conspiracy theories come apparently out of the woodwork, and they get passed around. And so she computed this graph on the right-hand side for the Orlando shooting. And she was looking at posts like this. You see right down here? This is a particular one, was Orlando shooting a false flag, blah, blah, blah. False flag means it is put on by somebody in order to influence public policy. So, for example, was this person really an FBI guy? That is, was he part of the government? That's a false flag operation. And so this is, in retrospect, this is clearly crazy. And actually, it was pretty clear at the time he was not part of the FBI, or not part of the government. But this kind of conspiracy gets passed around all the time. Her analysis showed that alternative narratives like this, false flag operation, have very different signatures. They have a different kind of way they get distributed between different people, different organizations. And here on the right-hand side, you see another one of those graphs where the size is how many posts each of those organizations made on this topic. And in particular, here's that same graph as color-coded by the narrative stance. That is, whether or not, if it's red, it was a denial. It was saying it was not a true story. It was green, it was a confirming, saying yes, it was real. And white is, unknown, right? So the blue is strong support. The green is using this as evidence, and red is denial. Wow. This is, it's been shown after the fact, it's really not a false flag. This is clearly a conspiracy, crazy thing. What's been going on here? I will tell you one other story, then we'll take our break, which is another friend of mine actually was a TV reporter at the Pentagon on 9/11. And as you know, the 9/11 terrorist planes were flown into the Twin Towers in New York City. And one was flown into the Pentagon and one in Pennsylvania, the field in Pennsylvania. And he was actually at the Pentagon. He was on camera on the far side of the building, away from where the airplane flew in. This is my friend Jamie McIntyre, and he was there reporting. And this plane flies in, boom, right? And he says on camera, this is on CNN, he says this on camera, he says, from where I'm standing, people keep saying a plane has flown into the building. I see no evidence that a plane has flown into the building. Okay, that gets broadcast. He then walks around with the cameraman to the other side of the building and says, oh my God, a plane has flown into the building, right? Remember, when he did that first broadcast, he was on the wrong side of the building. He walked around, he then broadcast and said, yeah, a plane flew into the building. We don't know what's going on, but this American Airlines flight flew in. Right? Interesting. He cannot get the conspiracy people to look at the second video. So as you probably know, there's a huge conspiracy theory that the government actually flew the planes into the buildings and into the Pentagon and so on. And what he has found in his analysis of social media and how it's propagated is that there are people who have a vested interest in one particular conspiracy story, and they don't want to know about the rest of the data. And you see the same kind of thing here in Kate Starbird's analysis. Alternative narrative people, that is, people who are supporting conspiracies and so on, find a network of like-minded people, and they stick with them. They stick with them, and they don't look at the alternative stories. Okay, I'm going to stop there. We'll take a quick 5-minute break, and we'll start again at just right after 5 after 5, okay? A few papers here to read, and I'm going to